in a language in order to get that the robots can have a smart communication between them for optimize large-scale optimization system. Okay, this is an idea about the state of the technology. You can see before, many years ago, more than 50 years, Newell and Herbert Simon, Nobel Prize in Economics, they felt that the situation is to say that there are now in the world machines that think, that learn, and that create. Moreover, their ability to do this thing is going to increase rapidly until in the visible future, the range of problems they can handle will be coexisting with the range to which the human mind has been applied. This vision have more than 50 years, more than, okay? This is a short resume of my life, and now we begin with speaking about the Industry 4.0. I think that the state in this moment is that we have robots that are autonomous and that work coordinately, that have synchronization to work together, but then speak between them. In the future, we need that the robots can speak between they, because it's necessary to have smart communication, to have more power for the decision-making aspects. The people, many scientific think that this possibility about that the robots speak in real time is we can get it in 20 years or more. However, I think that the knowledge accumulated by humanity is ready to permit that we can develop a smart language oriented to robots that representing many aspects of the world, can speak together and work together in real time according to the Industry 4.0. And this is a resume about the book that I am writing in this topic. The people can take the information. Here we have the Wi-Fi, the internet link to have the draft version of this book. The industrial, now we speaking about industrial revolution. These are the 4 revolutions that we consider. Okay, we are interested in the 2 last revolution. The 3rd revolution, that is the computer and automation revolution that produce in this moment robots. Robots that can work in automatic form, but they can speak between them, okay? With this revolution of the economic, it was called by Peter Drucker as the knowledge revolution. Many years ago, more than 50 years, he wrote the book, The Age of Discontinuity, and he speaks about the knowledge society that create a new type of work, the knowledge work. Okay, that is in the actual state, we think that this is the real state for the more, for the professional, more productive. Okay, then we have 2 types. We need to make a difference two type of organization or two enterprises. The intensive information organization that value his focus is the evaluation of data. And they produce in this moment the entrepreneurs, people that is working with this, with the big data, with the information intensive process. But we have another type, see, of knowledge that is of enterprise, that is the knowledge organization, intensive knowledge organization, that are the oriented to produce knowledge. Okay, an example is the vaccination for the coronavirus. There are two types of enterprise: the enterprise that can produce the vaccine, okay, for the coronavirus, and the another that they can use this type of new knowledge, okay, and this is the innovator. This type of knowledge produces the innovator. Now, in the fourth industrial revolution, we need to integrate systems. Then we need to see two robots speaking between them. Okay, this is the big difference. Okay, we will have smart factories, big factories that we can create a virtual copy of these factories of this physical world and to make the best in quotes decisions, okay, in real time. We need a higher level of intelligence, okay, that is oriented that two robots can speak within them. We see the difference between optimization and synchronization. In synchronization, we have many robots that know for example, for a production line, one robot knows what happened when he finished his work, and the next robot know what happened when the previous robot finished the work. They take the part, for example, and then he make his activity and produce in a synchronization way, produce in the line factories. This is a problem solved in this moment. But we need in the cyberspace, we need to integration. Then we need that all the robots and all the robots can speak within them. It's similar to what happened with the human beings. Okay, we can speak with any being, with the then we can produce optimization in real time. We decide in real time. Okay, this is real time, is clear, distributed, that is oriented to the take decision in a distributed form. Okay, many agents take decision oriented to make optimization of the whole of the system from taking an holistic point of view of the optimization, a condition to have the best, in quotes, factory, the best supply chain, the best hospital, the best. Okay, this is the big difference between synchronization and between smart communication to obtain real-time distributed optimization process. Now, it's important to understand what happened with the mathematics in this moment. Okay, and I speak about mathematical revolutions. The first revolution was the arithmetic, many years ago. The second big revolution and a transcendental revolution for me is the algebra. Okay, the algebra, the revolution occurs in 1800 of our era, okay, and was developed by the scientific Iranian Khawarizmi. Okay, but the main part is that, okay, we can, with algebra, we can make models. With arithmetic, we can make accounts. We can produce numbers, but algebra produce models. This is the big difference. And this difference was understood by Alfred North Whitehead, England physics, that told algebra is the intellectual instrument which has been created for rendering clear the quantitative aspect of the world. Okay, we have a big difference between two types of algebra. The school algebra, the scholar algebra, okay, that all people learn in his first years of education. But professional algebra, that is the algebra that needs the engineers, that needs the mathematical model, physics, the economists, the engineers, okay? We need to make models, and it implies a profession, okay? It's different, it's very different. And the main support of the algebra is a transitive law that is say that an algebraic model produces join with another algebraic model, produce a new algebraic model. Then it is very convenient because we have a standard to make a join of models, see, to join problems and to try to solve with this ability the real life problems in this moment. This aspect is fundamental in to establish a protocol of communication protocol between robots, because the robots are related with models, with problems, mathematical problems expressed in algebraic forms, and they can speak between them. We can see this. Okay, we can say that if we have a control system, we only have one and only one representation of the model. Okay, when we reduce the equations, we have for all the people that work and make a good, correct modeling has only one representation. This is fundamental. Okay, then we can say that the algebra established a new world, not a gap, a new world between the people that learn algebra with the people that don't learn about algebra. I think that this is the main gap that we have for more than 1,000 years. Okay, the second math revolution is an aggregate revolution. Maybe this revolution may include several revolutions, math revolutions, that we can say that the impact is that the impact is that we can make models, study the dynamic part of the models, the continuous evolution of the systems, and the optimal condition oriented to obtain the optimal point of a mathematical problem. And we have this occur with Newton and Lagrange and others from more than 500 years ago. The next part of this revolution, the end part of the revolution, is the model optimization. We have two types. We are speaking about optimization. Then we have the model optimization that is oriented to sequential processing. Okay, and it begins with the algorithms developed by Kantorovich and Danzig, and mainly Danzig with the simplex method. All the engineers many years ago learned about the simplest method to solve linear programming, because, for example, 40 and more years ago, we need to implement the code to solve the problem. Okay, when I begin to work in engineering, mathematical modeling, I need to develop a simple algorithm because we don't have a commercial algorithms, we don't have the production that we have actually. In this moment, the situation is different because we have commercial organization that produce, that his business is to produce the best solvers. But the end of this process, the model optimization is the production of the solvers to solve many formats of optimization problems. Okay? And then the resume that we produce the optimization problem that include an objective function and a set of constraints, and that have an input and output. All mathematical model of optimization have inputs. We can, if we see the formulation from algebraic point of view, we have sets and parameters as inputs, and we produce primal and dual variables as outputs. This is the solution. This is the, in quotes, the general solution of an optimization problem. Okay, and with these principles, with this idea, we begin to understand that the machines can solve problems that the human cannot solve. For example, the Sudoku. All humans can solve a little Sudoku, 9 by 9 Sudoku. But when we have industrial Sudokus, in this case, 25 by 25 Sudokus, it's impossible to try to solve this problem for a human person in a finite time. Then we need models. And for the models, it's very easy to solve the problem. It's very, in this case, the model is very simple, and the model solves the problem. Then we understand that the algorithms, the robots can solve the problems that we cannot solve the human people. And this produce this type of structure. We produce the basic solvers to solve the different problems, optimization format problems, okay? And we begin, and this in this moment, this is a standard, we can say, that to solve problems that involves decision processing. In this case, we have a web page that say vision-based of artificial intelligence model solves Sudoku at a glance. We can see more. Okay, for this, we need an algorithm. In this case, maybe a mixed linear programming algorithm that solves the problem. For another part, we have a technology and another type of algorithms that produce the pattern recognition of the image. Okay, then with the appropriate algorithm for pattern recognition, it's possible to establish the Sudoku, the elements of the Sudoku that are different from blanks at the beginning, and we can solve the problem. Okay, the processes, we see, the robot see an image, convert the image in a matrix, okay, send the matrix to a mathematical programming, mix it linear, and the robot solve the problem and send to the robot the solution that are the primary variables. And it's a decision process because they select which are the right values for each blank cell in the Sudoku. Okay, then we can begin to speak about neural nets, but I think that we can see a special neural net that I call a smart neural net that involves more than the traditional neural net, more knowledge than then because they have mathematical models involved and they have a function. In this case, we have a neural net that solves Sudokus, okay? And it may be in an algorithm, a heuristic algorithm, or maybe a mathematical program algorithm. I prefer the mathematical program algorithms. At the end of this is the actual era that we are speaking about analytics and advanced analytics. This begins from the book of Davenport and Harris in 15 years ago, and they say this is a vision of IBM, but they classify the analytics in three parts: descriptive, predictive, prescriptive. Prescriptive is optimization, is the best of the best of breadth. Okay, that in this moment for Davenport, the state of the art finishing optimization. For IBM, 5 years later, the state of the art is stochastic optimization as an standard. Okay, that means that we can solve the problem of stochastic optimization when we need. Okay, we have another type of algorithms, but in this moment we are oriented to put to establish a protocol to the robots to try to speak about decision making, and decision making imply optimization, imply prescriptive analytics, and then with this ideas, okay, the actual smart organization is based in models. And smart organization believe in models, don't believe in mental models, in Excel spreadsheets of similar. They believe in models, okay? And we can say that we have another new war, another gap between the humans and the algorithms. Finally, we have the math revolution oriented to parallel calculation. Okay, they begins many years ago when Danzig and Wolf began to speak about the decomposition principle, and then 2 years later, Professor Benders, begin to speak and write about partition theory. See, I think that the theory of Bendel is fundamental. I think that this is at least as important that the simplest method of Danzig, is my opinion. And posterior, Van Roy developed another principles that he called cross decomposition, oriented to make mixing of this decomposition and partition theories. Okay, and this is the base for the parallel optimization, parallel computing. Why is important parallel computing? Because the actual computers all are parallel. This is a problem solved. Okay, this is a future. For the short future is computer that all are composed by multiple processors. Okay, then the idea about the idea of Bender, for example, was to divide the problem. We begin here to divide the problem, and we coordinate, and we establish a conversation between these two levels. Okay, the level coordinator, we can call the level coordinator level, send to the subproblem level primal variables, and the subproblem send to the coordinator dual variables. Then we can see that the duality theory is fundamental. It's fundamental to establish conversation between problems. It's the key for all that we have, we can develop. It's important that all the algorithms, formal algorithms, exact algorithms, has relation with duality theory. All is important. Then we can say that, okay, we can put, using duality theory, we can put two different problems to speak between them, two different rows, or two different smart neural nets to speak between them. Okay, in which we have the smart implies that we have here more knowledge than a simple neural net. Okay, This is the case of vendors. This is the case of Lagrangian relaxation. The difference between the two large-scale technologies is that in vendors, the coordinators send primal variables and obtain dual variables, and in Lagrangian relaxation, as the coordinators send dual variables and obtain primal variables. Then there are some different to the process, but the focus is the same, to try to divide the problem to make partition and decomposition of the problem in order to have problems more easy to solve. Then we can build with this structure our roadmap about optimization. We have the basic solvers. Okay, this is the central part. Then we have the large-scale technology, and at the end, we have the real two aspects that are very important: stochastic and robust programming, and asynchronous parallel optimization. Solve problems in a large machine with many processors. Okay. There are one advantage about the large-scale technologies is that they produce a speed up of the solution when we make the comparison between the simple solver with large-scale optimization technology. In the when the complexity of the problems grow, okay, the advantage, the speed up of the large-scale optimization technology is grow. We grow exponential. Here, in the many years ago, when I begin to work with the large-scale optimization, I need large-scale optimization to solve the problem related with put the problem in the memory, in the RAM memory of the computer, because it was impossible to try to put in a short computer, in a mini computer, a very big problem, okay, for the epoch, okay. Then the speed of solution is the combination of the basic algorithms and the large-scale technology. In this moment, the basic algorithms, the basic solvers, are commercial, and they are growth very accelerated, very rapidly. Okay, and here we have the large-scale methodology that are growing in the academic part, but are not growing in the commercial part. And is different. There are applications that use large-scale technology in the commercial part, in the solution of real life problems, but this is not the standard. The scope of the composition and partition theories for large-scale optimization imply that I can divide the problem in many levels, and many subproblems in order to atomize the problem. Here, this is the basic atom of this problem. The rest of the problems are coordinated, but all have the same are maybe mathematical programming problems, algebraic models then, and we can coordinate all very easy because they all speak the same basic theory that is algebra. We can see this from another point of view, and we can speak now about the family of problems, different types of problems that put his solutions and take this input and put the output variables in database online, offline. Okay, this is offline in a disk, and this is online in RAM memory. Okay, then we can build a new theory in order to generate a next level of artificial intelligence. The upper level in this moment, I think, that is the hypothalamus, because this is the hypothalamus human beings. Okay, we have nets of neural nets, okay, that store the information in a historic system in the hippocampus, exactly, and all the neural systems of neural nets take the information and help the human to make decisions in real time. Then we have another gap between traditional optimization and large-scale optimization. The parallel processing generates another big gap because this is the evolution of the computer. We begin with the abacus and begin the computer with the machines in 1945. Okay, and now we have the quantum computers. This is the history. In the beginning, we begin writing the problems, writing the code of the algorithms in cards, in perforated cards. Then the capacity of the model in this epoch are related with the capacity of the man with work with boxes of instructions. For each instruction, I need a card. In this epoch, I write programs using this methodology. Now we have that there are a correlation between the parts of the computer. This is a resume of the different type of components, computer components like tensor processor, graphic processor units, CPU central processing units. They are related with the different type of device and the composition of parallelization, okay? For example, for large-scale methodology, we need CPUs. For algorithms, in this moment, we need TensorFlows and GPUs. The people are working to have a very, very rapidly and condensed algorithms to write in these little components. And the matrix operation are related with GPU, the array processor of many years ago. And the difference between the parallel and synchronous is very big, okay? It's very big, it's very different, okay, to solve the problem using a parallel computation. This is the time, this is the relation between the times without, in blue, the time without the parallel, and these little bars are the time using parallel. But there are two aspects that we need to consider in parallel optimization. One is the speed, okay? It's significant, and the speed up is very important. But the another is the precision. We can solve the problem with more precision than in the past. This is the type of error of a risk model for stochastic optimization. The error in the estimation of value at risk and conditional value at risk related with the number of processors that I am using. And this implies this number, that is a percentage, is more than the percentage, are the utilities of a company, are the risks of the company. Then errors in this estimation may be the life of the company, the life of the enterprise. Then now we have the quantum computers. It's a new era. Okay, I don't learn about qubit. I don't understand good how work the qubit, but I see, and I know that in the future the difference between with qubits or without qubits, this is the order of the speed up of the computer. Then, and the speed up of the computer is the real time of solution that we have to solve very complex problems. Then we have in this moment, we need to multiply the speed of the computer technology, of the basic algorithms, and the large-scale methodologies to have the real speed of solution and this is the limit for the problem that we can solve. Then we have another gap. Now I will speak about enterprise artificial hypothalamus. And the hypothalamus is fundamental for the human being, okay? At the right part, there are a short description. But what's happened in the modeling? The first type of modeling was we can call it top-down modeling. That is oriented to have a good idea about how work the system as a whole, okay, and decompose the system in the atoms using empiric rules, because we don't have the theory and we can simulate the theory. We don't have the theory to make this, and we don't have the power to simulate this. Now it's very different because the actual modeling, I think that is the bottom-up modeling in which we begin to describe the atoms and we can integrate the atom as a system using scientific rules. Because we know we can describe how work the atoms, and we can describe how are related with another atoms, okay? And then we can describe how is the summation of all, okay? How work all the system. Then this is the orientation, because the atoms are the part of these problems that we can generate with Benders or with Lagrangian relaxation, okay? We can assimilate, or we can relate the atoms with the robots, okay? That solve problems that have enough smart knowledge, and we can establish very complex networks of robots trying to solve a problem. Then we can begin to understand this. We can think. At the beginning, we have only one system that integrate the board of directors, and integrate the business management of all the company. When we have this all integrate and we see this problem as an integrate problem, the first situation is that we can see what's happening between the parts. And it is very important to coordination in a real-time distributed optimization, where the distributors are related with agents that are autonomous to take decisions. Then we need to know what's happening between the agents. What's happening between the agents, which is the coordination that we need to get that all the agents work together in order to optimize the whole system. It is in the real life, we distributed optimization it's impossible in the real life. It's impossible to develop models integrated to solve the problems of real-time distributed optimization. It's impossible. I think that is impossible. Then the first part is to understand that, okay, when we divide the system, we can understand what's happened between the parts, between the agents, between the atoms, between the robots, between the problems. We can establish the communication that are related with the validity theory, okay, duality theory. Dual and primary variable is the interchange. A process is different in Lagrangian relaxation and in Benders, but are similar, the ideas, okay? When we have this, we can begin to divide the problems in order to get the atoms, okay? Another part that is very important is that the part in which we divide the system have enough information and have are not mathematical tricks, tricks, manipulation to solve the problem. It's more than that. It's an information about the system. For example, if we have this, if the board of director is the board of a country and is the energy secretary, okay, they have many subsisting electricity, gas, and oil, and it's normal that the people who work in economics, that is the people who see the long term, okay, use for little models, for academic model, use the Cobb-Douglas productivity functions. Cobb-Douglas productivity function is a type of function for to resume the how work system, the electric system, the gas system, and the oil system. Normally are related in the with Cobb-Douglas. They speak about the factors, see, work factors like human force and capital and technology that are converted in products. Okay, this is academic because we have 3 factors or 4 factors and 1 product, or 2 products or 3 products. But the reality of a company and the reality of the world is that we have many factors and we have many products. Then which is the function, for example, in vendors of the subprograms. The subprograms are they produce the Cobb-Douglas productivity function. This is, they have the description of the system and they can produce to evaluate points of the Cobb-Douglas productivity function. Okay, this is when we study this type of approach, we get this. But what's happening with the technical aspect of the mathematics? Okay, the subprogram, the vendor subprogram cannot produce all the points of the Cobb-Douglas productivity function because the number of points are infinite. Then the function of the subprogram is to produce smart information about the Cobb-Douglas function. Okay, they produce information related where the part of the Cobb-Douglas function that is used to obtain the optimality. For example, we can say that we have a quadrant and we have the upper and lower part, and we have the right and left part. We have 4 quadrants, but the system are work in the upper right quadrant. Then the function of the vendors subprogram is to produce this part of the Cobb-Douglas function. And then with this part and this part, they can solve the problem now. This is the idea, the central idea about the large-scale optimization vision. Okay, then we can make models. We have an experience developing a large supply chain model, but in reality, there are an hypothalamus of an oil company in which we work in this part. We develop a model for the oil production. We develop another model for pipe, different models with different characteristics. A model for a multimodal transport of oil products and oil refining. And we integrate all the models around the knowledge database. If we use in RAM, okay, we generate the equation to coordinate all the models, and if we use this, we put all the information in this. Then this new vision, that we have, the parallel optimization is divide the function of the company in different processors, each processor with the function related with the work, with the area of work of the subsystem. Okay, in this case, sectors. There are another point of view that is important. That is, when we study the partition and the composition of a system, we have many points of view that are similar. We can see the point of view of the regions, because I think that is, I prefer to see the system as a whole system, as the union of a set of regions, or I can see the same system as a group of sectoral models. Okay, and then we have here electricity, gas, and oil, or I can see the system by divided by function, production, marketing, maintenance, for example. It's the same system, and this is valid for all systems. Then it's possible to develop models that have multiple points of view, okay, that we can integrate in a similar way that the hypothalamus of a human integrate information, because when we are taking decision, we are not looking only one point of view. We are looking for several points of view. When we drive a car and we are looking, see, many different aspects, the type of road, the amount of traffic, the climatic state. Okay, then all this information is about the same process, but have different information, and we can introduce this in these models in order to solve the problem, considering many points of view, and to solve the problems with more robust point of view. Then this may be a vision of an artificial hypothalamus. Okay? In which we have business or functions, all of these are related with mathematical programming, or have communication with the database, with the hippocampus, and they can solve as a glance a real problem. This is only a problem of scale, because the process is similar to the Sudoku. It's similar. We see the world through big data, so through Internet of Things, and we produce the data to the models, and the model produce the solution in real time, all working together. Then I say that this is a new type of revolution that we are beginning to live, okay, and that we need to live, because it's the next step to put two or more robots to speak with them. Then we can speak about communication mathematics. Okay, I go here. This is there are a document with this information. We can see, go to the image. Okay, we have in this, we can begin thinking that we have two types of mainly types of large scale methodologies. Bender theory, that is a primal technique, okay, primal factive feasible. That means that the work of the system is the feasible in the primal feasible area zone, okay, and we make the control, the coupling by the quantities, okay. We have another type, that's the Lagrangian relaxation. I say that is complementary. This is a dual technique. That means that he works in the dual feasible zone, okay. They meet optimality condition, and we can solve the problem with this. The problem of Lagrangian relaxation is that it don't work in the primal feasible zone. This is a problem, because if we finish the process in a moment, we don't have a solution. We have an optimal solution, but not a feasible solution. It's different with the Bender's theory, that we have a primal feasible solution. but okay, they work. We can resume this in this part. Okay, we can the model, divide the model with many subproblems. Okay, 1, 2, 3, 4. Each subproblem is the error. We have error subproblem here. Each subproblem is related with a robot, with the agent. This is the, for example, the financial vice president. This is the operation vice president. This is the general manager of the business one, and this is the general manager of the business two, and this is the time, the operation of the team. Okay, then we can make many partition decomposition approach. Okay, then, but all have the same. They have some problems. They have robots or agents. Okay, then we can say that for we speak about the database, a knowledge database. See, knowledge database in which we store all the information. It's time that the robot finish his work. He put in the storage database his information, its information, okay, and take new information, okay, and the result is a transformation function that depends of the robot. Is different the transformation function for the robot one that from the robot two or any, and it's different the transformation function if we are using Lagrangian relaxation or Bender relaxation. We can use the two types of methodology or large-scale methodologies simultaneously, like proposed Van Roy in his work called cross decomposition. Then we have many problems, okay, that produce information depending on the input and depending on the type of robot. Some include cutting planes, Bender's cutting plane, and the another includes Lagrangian cutting planes, for example. But we can use and introduce in the same way the protocols of communication using, for example, Dancing Wolf. Okay, then a robot, a problem, see, take the information of an historic database that begins in zero, in time equals zero, and have his transformation function, and produce a set of values that in this presentation we call primal and dual variables. Okay, when these variables go to the historic database that begins on some moment, see, are empty, and they are storage the information of 4 robots. In this case, the information of the robot A and the information of the robot B. It's important that we don't need that this produces information may be asynchronous. We do not need to be synchronous. Okay, we can solve this in a synchronous way that is the real time, and this is the real life. Okay, then we can, using in large scale technology, we can synthesize the communication using transformation function and storage, see, of information that we produce, and we can store this information in any type of device, maybe a RAM memory or maybe a disk memory. Okay, and we have the same idea that we present. I think that here we have a new gap, a new world. It's very different to think the world as a world problem, okay, but standard mathematical programming, that we implement models to solve a problem, that we can, when we develop models to work together in real time to represent agents, okay, to solve the problem. Examples of this, very two types of examples, a short example and a large example. In the first, okay, it's based in the, all is based in a top-down, see, a modeling approach. Okay, this is the case of a dispatcher of routing for vehicles, for trucks. Okay, traditionally, the people, the dispatcher, all days at any hours, at the fixed hour, for example, 8 o'clock in the morning or 12 o'clock in the night, he make the routes, he assign the vehicles, he take information about the travel times that it has, and they generate a route. But, and this is the BRP problem, and each problem has related for each trucks is a TSP, travel salesman problem. What happened with Waze? That is this. I think that is the standard, okay, of the big data in traffic in this moment. For example, in Latin America, in Europe, all people. I think that the majority of the people use Waze. We use Waze. Okay. Now then, at 8 o'clock, the dispatcher may be may be generating the route. But when any truck, any vehicle go to arrive to a client, okay, in this moment, the vehicle can go to Waze, see, to obtain the best, the best information from Waze, and they see and the vehicle can recalculate the route. And he solved a problem, a PSP problem, and he recalculate his route, because we know that the travel time is, say, the forecast of travel time is very, very, very difficult. Is okay. Then, and we have an intelligence device here. We have phones, we have iPads, and we have computers, videos in the trucks. Then we have the information. It's more, if the truck detect that he can go to any to a client, specific client, I can inform to the dispatcher, and the dispatcher may be adjust according to the situation and to the business. This is an example. Very easy, I think that is easy to understand. We have another type of situation. For all people that live in large cities, the problem of traffic is very, very complex, because we don't have the enough information to know what happened. The problem is very easy in mathematical form. And when I say the problem, I am speaking about to fix the travel, the time of the semaphores, okay, the light times for red, yellow, and green, okay, and to coordinate all. For a short, see, for a small region, it's easy, and it's not complex mathematically. But when we consider all the city, it's impossible to solve the problem in real time. We need hours to try to solve the problem for 1 hour. It's impossible. But we can change the approach. We can see the approach, we can divide the approach by zones. We have a traffic control center, and now we can coordinate the zones and the times. And each time we send information, the information that they all have, okay, to make the adjust of the decision dynamically. This is another case in which it's not necessary that these types of partition, it's possible that we can use vendors or Lagrangian relaxation that we need to customize Lagrangian coordination or similar any. But the idea is you can divide the process. You need to establish communication between the robots, and you can solve a very large problems that previously you cannot solve. Then in the future, your industry 4.0 organization will be based in real-time distributed optimization. This is a big change. It's the time to change the traditional application. The traditional application was mathematical models to solve problems, specific problems, and to coordinate the models, coordinate the model not in real time, offline, and with no automatic process. Here we have the advantage that we have a standard. If we have all the models running under the mathematical programming approach, it's possible to generate all the system with the same ideas from use primal duality theory to coordinate the problems, the robots, okay, and to divide the systems and to develop a standard protocol. It's important that to be commercial, we need standards. Okay, the another part, the end, here we speak about optimization per systems. It's important for the people that we grow in the way to that the experience was not lost. Okay, then we need, as any expert system, that the expert stores his communication, his knowledge in an expert system that is a computer system oriented to the non-expert user or beginner user to learn rapidly and to go to use these ideas. Then it's important that to solve this. And then there are 2 points of view. One is to store and reuse the mathematical components. That means to reuse mathematical models. Mathematical components of a model are equation, and an equation may be many models, and a model we can part of a big model. For example, the electricity and gas. The electricity is a model, but electricity and gas is a big model, and electricity and gas and oil is a big model, and I can put together to work. And this is one need. The another need is the results. We need to store as the result. We see that the robots need to continually optimize, then they need to store us all the information and to reuse the information each time that he must solve a new problem. And it is valid for the standard large-scale technology like vendors and Lagrangian relaxation. They work storing cutting planes that are included in the model each time that we have a new loop in the solution process. What is the meaning? What is the functions of text? All that I say here was developed using Optex. I am not an academic. I am an entrepreneur. I have developed algorithms. I develop Optex, and Optex helped me to develop a methodology that now we can call mathematical 4.0. All the thing that I am speaking was thinking in the beginning using Optex. Then first is that this is oriented to a new way of the advanced analytics, and more precisely in prescriptive advanced analytics. Okay, it's oriented to make the division, to make easy this type of modeling because we think that is the modeling that we need in the future. Okay, at the end, we need the robots in a general world that communicate with another robots and that can assume function. For example, I can a super robot that maybe produce the analysis that standard in this moment are producing the board of directors. The difference are that the model run continually, and in this moment the models run eventually. But in many companies, the board of directors use mathematical models, see, or to coordinate all and tell to the organization, sub-organization that use mathematical models. It's easy to see examples in the electricity, gas, and oil of companies that have models, and if I have models and I integrate all the can integrate all the models, then I have an interface and artificial hypothalamus. These are the main ideas about OptX. The real main support is algebraic programming, mathematical programming, because it represented the real system. Okay? Something that have OptX. For example, OptX is a cognitive robot from the point of view that he writes the algorithms. It is very important. When we see the computer that use cards, perforated cards, I don't know if it's correct in English, but in the beginning, the computer uses cards, and the capacity of the programmer was related with his capacity of manage boxes of cards. It's possible to say, okay, I remember when I was a student in 40 years ago, 45 years ago, when I have 8, 9 boxes of 1,000 cards. Then my biggest model was 9,000 instructions. The next step is to make programs. And we have, then we change the lines of code from write the code more easy, that the cards, okay, more easy, but limited by the amount of the line that can write a computer program. Now we develop OptX because we need to develop very big problems. This is very large problems. If you don't have the power, you can develop very large problems. Then in this moment of test, write infinite lines, number of lines, see, of perfect source code. The alternative is limited lines of good source code, because when we have humans, we have good. When we have computer, we have in quotes perfect. Then this is the way to propose to make artificial hypothalamus in this moment. This type of technology is open in this moment. We are trying that the people learn about all of this, about OptX and about the artificial hypothalamus, and if the people learn about it in 6 months, he can work making artificial hypothalamus on large, very large business. And then this the difference between the computer programmer, see, that is the traditional approach, with the cognitive robot that writes the programs, are very, very big. For the people interested, we offer a free course about OptX that is related with mathematical 4.0, okay, in which we see the mechanical part of OptX, and we see the smart part of OptX, that are the artificial hypothalamus. Another part that we invite the people interested is about the Atenea project. Atenea project is, we think that in the field will be the first being artificial hypothalamus in the crowd, okay? And it's an open project. Any type of organization can work in this project. Okay, I think that with the time we will be oriented to develop a non-profit organization to drive all like this type of ideas. And we have in Atenea project 3 goals. One is to develop a regional planning hypothalamus, okay, for all the cities and rural regions to integrate, to make decisions and to integrate this type of information that is not included ever in the concept of smart cities, okay? But I think that the first step in the smart city, the planning of the territory. And we have in the US another 2 projects, that is the industrial hypothalamus. We think that we SME enterprises, small and medium enterprises, okay, and the electric hypothalamus more oriented to smart grids, but can include all the model that we have. Why we can work in this? Because we have all the models developed in Optex, and we can offer to the people, to the area, to the people, to the organization, universities, research centers, interested people, persons, that we have this. Then it's very easy. We don't need to begin to make models. We need to begin to integrate models as the artificial hypothalamus point of view. Thank you for all. This was the webinar. Please send me the questions by the chat, and I send you the answers in the short time.